Hi everyone, welcome to week 11 of the course Fluid Dynamics for Astrophysics. I'm Suprita and I'll be taking this live session. We will begin by revising the material that was covered this week and then we'll discuss some problems which will help you solve the quiz problems. Uh, so this week we discussed waves in MHD and the parallel and ideas of sound waves were derived, were discussed again. So, to recall, sound waves are a consequence of compressibility. Remember that compressibility was what was required for sound waves, and the speed of such waves was the characteristic speed for small perturbations in fluids, right? And the speed was given by del p del rho. And if you remember, when we wrote down the equations of motion for whatever forces the fluid is subjected to, whatever body forces, whatever pressure forces the fluid is subjected to, and we linearized the equation of motion for the fluid, which means that we wrote down the equations such that the equations are linear in perturbations because we treat it in a perturbative manner and we say that whatever small perturbations arise on top of the background uh, uh, pressure and density, these perturbations are small, and so the equations will have only terms that are linear in these perturbations. And then we move to Fourier space. We wrote everything in terms of omega and k, and we saw that the relation between the omega and k is non-dispersive, right? So these sound waves, once again to recall, they are a consequence of compressibility. So sound waves are compressible. The velocity of these waves gives you the characteristic speed for small perturbations in fluids, this one, and then non-dispersive. Then we move to waves in MHD. So we study these perturbations in fluids in the presence of a magnetic field, right? In the presence of a magnetized background. Once again, we consider a background rho, P, and B. These are the background density, pressure, and magnetic fields. We without loss of generality consider the background magnetic field to be along Z, and we see that the background quantities do not change in space or time. It is the perturbations that can change in space and time, and it is these perturbations that we want to study. These will propagate as waves, right? And we see that the background velocity is zero. This is exactly what we did when we studied waves in fluids. And for now, we consider that the y direction is a special direction because there are no derivatives along y. Nothing varies along y. And we will see as a consequence, we get a special mode for all of the perturbations along y as a consequence of this. Okay, all right. So we'll follow the procedure we used. We will linearize the equations of motion. What are the equations now we have to consider because of because of the presence of a magnetic field? We have an extra induction equation. That's the additional factor. And we'll have to consider an extra force, which is the Lorentz force, in considering the momentum conservation equation. So the mass continuity equation was this. Linearized form was this. This structure is the same as the one without magnetic fields. There are no extra terms arising in the mass continuity equation because of the magnetic fields. But in momentum continuity equation, you'll have a Lorentz force term, which is basically this. This is the J cross B force term arising because of the magnetic field. This is the full equation. Now we will linearize it to first order in perturbation. Uh, so let's look at the first term. To linearize this, let's look at it term by term. So the first term has a V in it. And this V is already the perturbation because we considered no background velocity. Hmm? So this will be changed to a rho dv dt, where this rho, where all of the quantities over here are the full quantities. This rho is the full rho. This rho is rho plus del rho, right? But when we linearize it, this rho will be written as just the background rho. We'll drop del rho. Why? Because then this term becomes second order in perturbation. Similarly, this term you see is already second order in perturbation because it's v square. Then you have a gradient of p, but we know that the background p, this p over here, which is the background pressure plus a perturbation, the gradient acting on the background will give you zero because the backgrounds do not vary in space and time. So then this becomes gradient of del P, the perturbation, the pressure perturbation. Next, for this term, you see that the curl of B will give you 0 when you consider the background B over here. So you consider del B, and when you do that, this term already becomes first order in perturbation. So then this will have to be the background B. So when you linearize the momentum continuity equation, this is what it becomes. Next, you also have to consider the induction equation because now we're considering MHD. The induction equation to recall was del B del T is equals to the curl of the velocity, cross product of the velocity with the magnetic field. When we linearize it, we'll first have to consider this term. And of course, the background fields do not vary with space and time. So this B over here will be the perturbation. Then this V is already first order in perturbation because of this V. So over here, this B will be the background B. So we have linearized the relevant equations of motion. Next, uh, to see the fact that there are in fact three different modes. One is the Alpine mode and the other two are magnetosonic modes. What we will do is we'll split it into components that will help us identify these different modes. Okay, so we split it into XYZ components. We write these linearized equations in XYZ components. Uh, to do that, first look at the linearized momentum conservation equation. There is a curl of delta B cross B, right? So let's first evaluate curl of delta V. Curl of delta V in Cartesian coordinates is given by the determinant of ijk del x del y del z and the three components of delta V. So once you compute this determinant, it gives you I cap, j cap, k cap components as this. The algebra is simple. You just have to follow the steps. It's lengthy but straightforward, right? So we have curl of the magnetic field perturbation. Then we'll have to take the cross product with V. We'll take the cross product with V, right? Now B, remember, we took it without loss of generality along Z axis. So if it's along k cap, the cross product of this term with B will drop out because this is the k cap component. I cap will give you I cap cross k cap will give you a minus j cap, and you multiply B with this. Similarly for this component, it gives you I cap. Okay, so splitting this equation in XYZ components, because now you have the X and Y components of this, what do you get? You get the X component will be rho times del T of Vx minus the X component of gradient of pressure perturbation, which is this, times X, the I cap component of this cross of delta B cross B. Similarly, the Y cap component, where notice that I have kept the Y derivative. This is just to tell you how it affects the existence of Alfvén mode, how it is crucial to consider that the Y derivatives of quantities indeed have to vanish for you to get an Alfvén mode. Okay, so I've kept the del Y, all of the terms. I have not dropped the Y derivatives from this term, from this cross product, and you have an extra term in the Y component over here, and the Z component is simple. Okay. And you also split the induction equation in XYZ. What do you get? So in the induction equation, you have a curl of V cross B. So we have to compute this term component by component. V cross B is given by this determinant. So you have I, J, K. You have Vx, Vy, Vz. And B only is non-zero along the K cap component because we took B to be along K cap. Okay. All right. You compute this. What do you get? You get this. Very simple. Only I cap and J cap components remain. Okay. All right. Then we take the curl of this. To take curl of this, we have I cap, J cap, K cap, del x, del y, del z. The I cap component over here and the J cap component over here. Okay. We compute this determinant. you will see that it is this. Where once again, I have written the y derivative term in red and I have not dropped it to show something. Okay, this is the full term. I have not dropped anything. Then what I'll do is write the xyz components of the induction equation. The xyz of the left hand side will just be del del t of bx, del del t of by, and del del t of bz, right? Not bx, by, bz, the perturbation delta bx, delta by, delta bz. Hmm? And then on the right hand side, we have all of the values I cap, j cap, k cap of the right hand side. So we substitute this over here. Okay. All right. Uh, okay. Now if you write down the xyz component equations of the momentum and induction equations, this is what you get. These are from momentum conservation. This is from the induction equation. Okay. Now you see that the y components of the perturbations Vy and del By do not appear anywhere else other than this. They don't they don't come with xz components of the perturbation if you drop del y terms. Okay, that is why they are special. That's why the y component perturbations are special, because you have said that y is a special direction along which my perturbations do not vary. There are no gradients along of any quantities along y. That is why you can drop these terms, and that is when you get uh, the y components of the perturbation to decouple from the xz components of the perturbation. Okay. In that case, if they do decouple, then you have this equation and this equation. And these two equations are decoupled from the xz components, but they're coupled in the sense that Vy arises in the equation of del Vy and so on. But then you can decouple this. You can decouple equation Vy for del Vy and get a second order equation. How? Uh, so if you write the y component if you want to write it as a second order decoupled equation, what do? Let's say you consider this equation. You act you act with time derivatives on both sides. On the left hand side, you get a del t square delta by. On the right hand side, you get a b del z of del t vy. But del t vy you can obtain from here. What is del t vy? Del t vy is just p by 4 pi rho del z of delta vy. Same thing over here. Okay, which gives you this equation. You have a del t square and you have a del z square. Okay, if you rewrite this b square by 4 pi rho as va square, this equation is a wave equation. This tells you that the y component of perturbations propagate along the z direction, because understand that in the equation of motion for del Vy, there are no other components, no x or y components. So what do? These y components of perturbation propagate along z as a wave with what velocity? With whatever comes multiplied to del z square. So the velocity of these y component perturbation waves is Va. These are Alpine waves. Okay, these are transverse because the disturbance is along y. These are y components of perturbation, and they propagate along z. So the disturbance is oscillating, the waves is oscillating in a direction perpendicular to the direction of propagation, which is along z. Z also being the direction of magnetic field. Okay, so and you can write the same equation for Vy as well. Okay, so what do you get? You get Alpine waves, which are transverse waves, which travel at the Alpine velocity. The Alpine velocity, okay, this should be v square. The Alpine velocity being v square by 4 pi, which is very analogous to the speed of sound, where the speed of sound was if you remember, it was sort of the ratio of the gas pressure to the density. Same thing here, just that you have a magnetic pressure over density. That gives your Alpine velocity. All right. Uh, Once again, if you take this equation and study it in Fourier space, right? So you write down the Fourier transform of, let's say, del by, hmm, and you trade these derivatives for omegas and k's, you get this relation. All right, that kz is the component of the propagation vector along z, along b. Okay, so clearly this is non-dispersive because in the ratio of omega by k, there is no dependence on omega. So these are non-dispersive. All omegas will travel with the same velocity, right? Also, any del p's or del rho's did not arise in the equation for the y component. So you do not need the fluid to be compressible for the propagation of these waves, for the propagation of alpine waves. Okay, so compressibility is not required. It is independent of the propagation of alpine waves, or the existence of alpine waves is independent of whether your fluid is compressible or not. All right. This was all about the y component of the equation of motion. Remember what we did? We considered the momentum conservation equation and induction equation. We linearized it, split it into xyz components, and we noticed that if we said that the all of the perturbations do not have any gradients along y, then the y component of these perturbations are like transverse wave solutions. Okay. Now what we are going to do is study the remaining components, x and z. Also notice that we did not study the mass conservation equation that we are going to take up now. Okay. All right. These x and z components will form what are called magnetosonic waves. Okay. They have a solution which are called magnetosonic waves. All right. Now we will study all of these equations in Fourier space, right? We'll trade all of the time derivatives and space derivatives for omegas and k's. Then the mass continuity equation, which was given by this, once again, we will trade all of the time and space derivatives for omegas and k's. So the del t's become I omega del rho. The gradient of v, which was something like del v, del x, I cap, plus so on and so forth. These del x will pull out a kx, right? So you'll have a kx, v, I cap, and so on. I should not put a vector sign over here. What this essentially gives you is a k dot v. Sorry, this is vx, this is vx, right? So all these terms give you a k dot v. Okay, all right. And then, of course, this in Fourier space, the in the exponential you have exponential of minus ik, so you have a minus ik with every component, and this gives you minus I rho k dot v. Okay. Next, we trade del rho for del p. And how do we do that? We say that cs square is del p by del rho. So then we can make the substitution, and we divide this equation by I omega. That gives you this. Okay. But remember, k dot v is kx vx plus kz vz. Can you tell me why? Why is there a ky vy not there? Because what is divergence of v? It is actually del vx del x plus del vy plus del vz. Why am I not writing this term? Because remember that I said that del y of any quantity is 0. Okay. I hope this is clear. I said that del y of any quantity is 0. So anyway, this term drops out. This and this gives you this. Okay. I hope this is clear. Please ask if you have any questions. Okay. So this is what you get. Just rearranging a few terms. The pressure perturbation is related to k dot v as this. Okay. Next, we consider momentum and induction equation, momentum conservation and induction equation. The x and z components are this. This is just I've copied it from the previous slide. Okay. Uh, Now we'll write this in Fourier space. We'll trade all of these derivatives for omega and k. The x component will be rewritten as I omega rho Vx has a minus del x delta p, and del x will give you a minus ikx. There's a minus sign already over here. You have a ikx delta p. Same thing over here. Same thing over here. Just follow the rules. This is just plain algebra. You'll get this equation. Okay. Rearranging a few terms, getting rid of this factor of I. If you rewrite this, you'll get this. Okay. Where here we have used the fact that delta p is this over here, and we've written this. Okay. All right. Next, we consider this equation, which translates to I omega delta Vx from delta t delta Vx. And from B del Z Vx, we get a minus IKZ VVx, which rewriting, getting rid of these I factors, you get this. All right. Next, consider this equation. This becomes a I omega rho Vz, and this gives you a minus IKZ, and there's a minus sign over here already, so you get a IKZ delta rho, and delta to remember is this, so we substitute this over here. Rearranging, you get this. Similarly, this equation. It's extremely straightforward. Let me know if you have any question over here. All right. So all of these, so this equation, this equation, this equation, and this equation is what one has to solve to get the solutions of magnetosonic waves. Okay. Uh, but to get some non-trivial solution for del Bx, Vx, and del By, del Bz, Vz, uh, if you write these four equations in four variables in terms of matrix, well, you can use two of these equations to trade del bx and del bz for vx and vz, and those two in the two remaining equations in vx and vz you can write in terms of this matrix. Okay. The middle steps are just algebra and they're not required, not necessary. They're just algebra. So I'm skipping over the steps and they're not very necessary. But you can rewrite these four equations. You can trade del bx and del bz for vx and vz and use that in the two equations to get this. Okay. If you solve for the determinant, okay, so to get non-trivial solutions for vx and vz, the determinant of this matrix has to be 0. You find out the determinant, which is basically given by this. You set it to 0, demanding non-trivial solutions for vx and vz. You get this equation. And you immediately recognize this as a dispersion relation. This is a relation of omega with k. You immediately identify this as a dispersion relation. And then to simplify this, to make sense of this equation, you define a variable, you study this equation in terms of the phase velocity, which is omega by k. All right. You divide this equation with k to the power of 4. This term gives you u to the power of 4. This gives you a u square. This entire thing gives you a kz square by k square. Okay. But kz square by k square is what? This kz is actually the component of k along b vector, b cap. Kz square is the square of this, right? But you can pull this k square inside the square, and this is just going to give you a k cap, right? So what is this? This is the angle between the propagation unit vector, and the vector along which b field points. Let's call that cos theta. Okay. So then this dispersion relation becomes this. Remember what is cos theta? Cos theta is the angle that the propagation vector makes with the magnetic field. Okay. Then the dispersion relation becomes this. All right. Uh, okay. Solving for this is like a quadratic equation in u square. Solving for that, you get u square equals to this. Okay. Where v is the Alpine velocity that we already wrote in terms of b and rho, in terms of magnetic field and density. We know what cos theta is, and so on. Okay. All right. Here you'll see that since this was originally an equation in u to the power of 4, sorry, since there's a quadratic equation in u square, you are bound to get two solutions, one with a plus, one with a minus. One with a plus, one with a minus. Now what do? We say that these two modes of corresponds to fast and the other corresponds to slow magnetosonic wave. Okay. How do we know the plus? The plus is the velocity of the u corresponding to plus is greater than the value of u corresponding to the minus. Because clearly this quantity has to be less than 1. If u has to be greater than uh, real. Okay. If u has to be real, then this whatever is under this root over has to be positive, right? And if it has to be positive, it comes with a minus, 1 minus. So this entire quantity has to be less than 1. So you automatically knows that the plus corresponds to a greater u as compared to the minus. Okay. Also, for this quantity under the root to not give you any imaginary parts, you need to have this entire quantity. You need to have this quantity in the denominator to be greater than 2 cos theta. Okay. Then you will have this entire quantity less than 1, and this root over is going to give you a real. That's where the condition that P equals to Cs by Va plus Va by Cs greater than 2. This equation was there in the slides. This is where it comes from, by demanding that U be real. Okay. All right. Uh, okay. Once again, in this dispersion relation, you will see that this U is independent of omega. So it's non-dispersive. Okay. But there's cos theta in U. Okay. There's cos theta in the relation of omega and k. Okay. Which means that it is anisotropic. First of all, it is anisotropic. Secondly, the group velocity is going to be different from the phase velocity. For sound waves, the group velocity was the same as the phase velocity. There was no theta appearance in the dispersion relation for sound waves, right? There was theta appearance in the dispersion relation for alphinic waves, remember? The same thing happens for magnetosonic waves. Huh? As a consequence of this, when you compute the group velocity, which you can get by doing this, right? It will have a k cap k directed, so radially outward directed component, and it'll have a theta component, right? You will see that it is not the same as this. V plus minus is basically this u. It'll have an extra component. So the group velocity differs from the phase velocity as a result of this theta appearance in the dispersion relation. Okay. All right. Now to make sense of this, what does one do? One takes the limit of Cs much greater than Va, or Va much greater than Cs, or magnetosonic waves traveling nearly perpendicular to B. What does that mean? That k dot B, which is cos theta, is 0. Then you can ignore this term. So to simplify or to make a few statements about this dispersion relation, to simplify this, what do? We can take the simplifying limit of Cs much greater than Va or Va much greater than Cs, or consider waves that are traveling perpendicular to the magnetic field. What does that give you? That tells you u fast, which is the u which comes with the plus sign over here, right? If this entire term drops out, what do you get? You get a root over of ca square plus va square, right? Because in this limit or this limit, either when you're working with very large cs or very large va, or perpendicular waves, perpendicular propagation to b, you can ignore this term. This term drops out, and then this u fast simplifies to just root over ca square plus va square. What does this mean? That in this limit, fast waves are isotropic. Later on, you will see that it does not actually matter, effectively, it does not matter whether you're working in this limit or you're working where V and Cs are comparable. Fast modes are mostly isotropic, very nearly isotropic, okay? And they travel with Cs or Va, whichever is bigger. whichever is greater. Okay. Slow modes, the ones which come with a minus sign, slow modes on the other hand, if you put in the simplifying assumptions, what do you get? You get, first of all, you can't just ignore this, because then this will just lead to zero. You can do better, and you can expand this. You can binomial expand this, and then you will see that this this term becomes this. Hmm? Performing a few simplifications. Let me know if this step is not clear. Performing a few simplifications, you will get this answer. Okay. So you do have theta appearance even under these simplifications in the slow magnetosonic mode. So what does this tell you? That slow modes are anisotropic, right? There's marked anisotropy in slow modes, and they will propagate slower than the sound or the Alpine speed. Whichever is does not matter which one is slower, slow modes will travel even slower than the sound waves and Alpine speeds. Because of this, right? If VA was much larger than CS, then you would drop this term and the CS will move up, but there's a cos theta multiplied to CS, right? So U slow will move slower than alpine or sound speed. Depends on which direction of propagation you are considering. Cos theta depends upon which direction of propagation you're considering, right? Later on, you'll see the profile and you will see that U slow is actually maximum along the direction of B. Clearly, when theta is 0, and you're considering propagation parallel to B, when theta is 0, this is maximum, right? And then U slow is given by whichever is slower, VA or CS. Okay. But in these simplifications, when you're considering this or this, okay, for the with the full dispersion relation, in general, you have all of these ugly terms, hmm? And then this profile was shown to you if you remember. This blue line was the sketch of U fast magnetosonic, this U fast as a function of theta, right? So if the wave were propagating, let's say along B, what would be U fast? What would be the value of U fast? This would be the value of U fast, right? If the wave were traveling with this theta, making an angle of this with the magnetic field, then what would be the value of U fast? This would be the value. This would be the value of U fast, right? This is what this plot tells you, and we'll see a few features of this plot. Okay. So let's say CS is equals to half of VA. We are considering CS equals half of VA. We'll put this in and see what value of phase velocity we get for the fast and slow magnetosonic wave. So U fast square, if you put in this value, you will see that it turns out to be this. Of course, there's a cos theta over here. Then what we'll do is we'll take two different limits of theta. We can either consider theta going to 0 or pi. It does not matter because it's a cos square theta. So theta, whatever theta, at theta equals 0 and theta equals pi, you have the same value of cos square theta. So at theta equals 0 or pi, what does u fast simplify to? It simplifies to this number. Now if you compute this, you will see that it's 1.8, which is very close to 2. So it's almost 5 by 4 VA square, very close to VA square. In fact, this is actually 4.444 VA square. Hmm? So you see that for theta equals 0, this the value of u is very close to VA. In fact, in this diagram, it coincides exactly with VA, right? But understand that for theta equals 0, this is very close to VA, where VA is this green line. Once again, so that there are no doubts, Alpine waves will propagate along the direction of B only. This is for illustration purpose. This circles are only for illustration purposes. The true Alpine waves will only propagate parallel to B with one velocity VA. There is indeed a theta over there, but the Alpine waves only propagate parallel to B. Hmm? Okay. All right. Next, we consider the limit where theta is pi by 2. So we are looking at this line, this propagation. Okay. So for theta equals pi by 2, u fast actually simplifies to pi by 4 va square. So you see that the value of u fast at theta equals 0 and the value of u fast at theta equals pi by 2, they're not that different. They're actually quite the same, right? So it's very nearly isotropic, even though we are not working in the simplifying limits of Cs much larger than Va or Va much larger than Cs. We are working in a limit where Cs and Va are comparable. We still see that U fast is actually very nearly isotropic. Okay. Then let's still work with Cs equals half V and see what happens to U slow, the phase velocity of the slow magnetosonic wave. You see that this will simplify to this equation. And then you take theta equals 0 or pi, theta equals 0 or pi, you will see that u slow is Va square by A. So it's much, much smaller than Va. That's why this is the value of the slow in this one. And for theta equals pi by 2, at theta equals pi by 2, u slow is actually 0. So it goes to 0, drops to 0 at theta equals 0. Okay. Same thing, you can same analysis you can repeat for Cs equals 2Va. I will not bore you with the details because we just went through it. For Cs equals 2Va, you plug this in over here. You get u fast square equals to this. At theta equals u pi, u fast square turns out to be 5 by 2 Va square times 1.8. Right? What is this? This is 5 Va square, which is much, much larger than Va square. As a consequence, you see that if Va is somewhere over here at theta equals 0, then at theta equals 0, the u fast will be somewhere over here, much larger. Okay. Similarly, for theta equals pi by 2, you will see that once again it's 5Va square. Once again, very nearly isotropic. Okay. So what do we conclude? Fast waves, they're very nearly isotropic. The fast magnetosonic waves, they're very nearly isotropic. No matter what uh, uh, VS, VA and CS you're working with, on what scales of alphinic velocities and sound speeds you're working with, the fast magnetosonic waves are almost isotropic. The slow waves have marked anisotropy. No matter what limit you worked in, they'll always be guided by B. The phase velocity will be largest parallel to B. Okay. All right. Then a useful quantity to keep in mind for MHD is this plasma beta parameter. Plasma beta is what? Uh, this is P by B square, the gas pressure by the magnetic pressure. Now, if you remember, Cs square was given by P by rho. Of course, there are factors of gamma depending on, because this is del P by del rho. If you remember, Cs square is del P by del rho. So Cs is actually gamma P by rho. And Va square we just saw, it's some B square by rho, right? So if you take the ratio, you'll get P by B square with some factors of gamma over here. Okay? But the plasma beta then basically is proportional to C square. This I shouldn't strictly be writing this. I should write this proportional to C square by V square. Okay. Next, this topic was slightly touched upon, shocks and MHD. This was not done in details because uh, this can get very complicated because as you saw in the lectures, a lot of there are a lot of complications involved because now you have many different modes as opposed to your normal fluid dynamics. In the presence of a magnetic field, uh, the waves tend to have a there are three more modes actually. Okay, so on top of your typical sonic waves, you also have your alpine waves, you have magnetosonic waves. There are two modes. There are fast and slow magnetosonic waves. So all of these are velocity scales. And you know that in normal fluid dynamics, we saw that shocks develop when the fluid velocities exceeded the sound speed, the speed of sound in the fluid, right? So when that happened, shocks develop. These discontinuities of pressure developed, pressure and densities and velocities developed. Okay, but now in MHD, uh, what is the velocity scale that we consider should set the limit beyond which shocks will develop? Now you have four different velocity scales, right? You have your usual CS, you have your alpine velocity, you have your fast and slow magnetosonic velocities. So, what is the velocity you should consider? The answer is that you can have all of these different kinds of shocks. Okay, so when the fluid velocity exceeds these velocities, you'll have various different types of shocks creeping in. Okay, so equations, or it was not studied analytically, some features were discussed of shocks in NHD, and we'll just very quickly revise through it. So just like we derived jump conditions in ideal MHD, which to remind you, if this was the shock, if this was the shock front, the shock was moving along this direction, right? So this is the pre-shock, this is the post-shock fluid, and the shock was moving in this direction. Then what we derived was the uh, ratios of velocity, density, and pressure in both of these regions. These were the jump conditions, if you remember. They were related to the Mach number, uh, which is the speed of sound in the pre-shock region, I think. Okay, so this was done in your usual without magnetic field, the fluid scenario without magnetic field. You can do the same thing over here. Uh, there you'll once again consider conservation equations. You'll consider the mass flux conservation. You'll consider the mass flux conservation like this, where you equate rho u in both across the shock front in the pre and the post shock regime. Then you had the momentum conservation equation. But now this will there'll be an additional term because you have the Lorentz force because of the magnetic field. That's really all the change you'll make to the momentum conservation equation. So what is the extra term? This, which is the magnetic pressure, and this, which is like the magnetic shear stress. Okay, so these are the off diagonal elements of the magnetic stress tensor. This was the diagonal elements. It was the pressure sort of the scalar term. Okay, so once again you'll equate this. You'll equate this across the shock front, and then you had also had an energy conservation equation. What you'll also have to keep in mind is the fact that divergence of B is zero. You'll have to impose this condition. What does that mean for the magnetic field across the shock front? It means that, well, if you integrate this across a very small volume element which passes through the shock front, you will see that this divergence of B dotted with the area vector will give you the B which is perpendicular to the shock, or rather parallel to the shock normal. So it gives you this component of B. And this equation tells you, it gives you the continuity equation that B parallel in the post-shock region is equals to B parallel in the pre-shock region. Okay, this is one of the constraints that you'll have to impose in MSD. Okay, you can also look at the discontinuities developed in the electric field. How do you do that? You consider in steady state the equation of curl of E equals del V del T. Okay, once again we integrate this across this surface. And what do you get? Since E parallel was zero, remember, we said that in the fluid frame there are no electric fields. Then we frame transformed and we related the electric and magnetic fields in the lab frame with the uh, with the fields in the fluid frame. And then we observed that E parallel was zero and E perpendicular was this, right? Uh, okay, so you will see that this is the component of V which is tangential to the shock front. right? So this is tangential to the shock front. And all this equation tells you what is E perpendicular. Also remember what is E perpendicular. E perpendicular is the component of E perpendicular to the velocity of the fluid, right? So what will that be? This is the direction which is perpendicular to the velocity of the fluid. And this actually gives you the tangential, the E tangential to the shock front. I hope this is clear. This parallel and perpendicular refer to the direction of E with respect to the fluid velocity, which is this. So E, which is perpendicular to this, is actually E, which is tangential to the shock surface. Okay. So what this equation tells you is it tells you that the tangential component of E is actually continuous across the shock front. Okay. And how do you get the tangential component? You cross it with n cap. Clearly. Why? Because n cap is along this direction. Taking the cross product of a vector gives you another vector which is perpendicular to this vector, right? And what is perpendicular to this vector? Any vector in this plane. That gives you the tangential component. Okay. So what we have done is we have related this component of E across the shock front. Okay. So these are your usual jump conditions. We will not complicate our lives by uh, relating this to other conditions and deriving the jump conditions, let's say, explicitly by figuring out the ratios of these quantities in the pre and the post shock regions. That is not required. All right. Uh, so, if and now to discuss the types of shocks in NST. If you remember, in the usual fluid scenario without the hold on a second. In your usual fluid scenario without the magnetic field, we studied, remember, parallel shocks. Parallel shocks being uh, the scenario where the velocity of the fluid is parallel to the shock normal. Okay. You could have also studied oblique shocks, which were more complicated, so we did not. Uh, over here, you can have over here in MST, parallel shocks are defined by the shocks where the velocity and the magnetic field are parallel to the shock normal. Okay. In this case, every other jump condition is the same as the your usual hydrodynamical situation without the magnetic field. But now you have the extra parameter, which is the magnetic field. So to find out the jump condition of the magnetic field, which we have actually already discussed over here, because you have to impose divergence of B equals 0 for any shock, what do you get? You get the parallel component of B in 1 is equals to the parallel component of B in 2, where 1 and 2 refer to pre and post shock regions, right? But since B, the only component of B is along n cap, there is no other component of B which is perpendicular to n cap, right? Which is, let's say, parallel to the shock surface, which is perpendicular to the shock normal, right? There is no other component. So B parallel is equals to B. So what do we have? We have B1 equals to B2. Okay. This was parallel shocks. Perpendicular shocks are the ones where the magnetic field is completely perpendicular to the shock normal. Okay, so this is the shock and this is the shock normal. You have magnetic fields along this direction. And let's say they're different in the two regions, in the pre and post shock regions. Okay. If they're different in the two regions, then clearly the magnetic energy in the two regions is different, right? So what is adding to the magnetic field? What is adding to the magnetic energy? You actually have flow energy converting to magnetic energy that gives you a different uh, value of the magnetic field across the shock front. Okay. And these shocks will propagate at the velocity V a square plus C a square with the fast magnetosonic velocity. These are just to be known as facts because this was not derived for you. So there's no way for you to know where this comes from. So this is for now just to know for facts. Okay. All right. The third and the final kind of shock that was studied was oblique shocks, where B, the magnetic field, can make some angle with the shock normal. And then it was told to you that if you're dealing with fast magnetosonic waves, right, then as the shock passes over the fluid, what it will do to the fluid is, so what it will do to the fluid is in the post-shock region, B will be bent away from the normal. So it will actually add to the tangential B, B tangential to the shock surface. And what that will, it will increase B tangential. And what that will do is it will eventually increase B. Because B is the total magnetic field is the sum of the two components, the parallel and the tangential. The parallel components are continuous because of this. But the tangential components, we know for a fact that in fast magnetosonic waves, B is bent away from the surface normal, which means that B tangential increases. I hope you understand why. Let me know if that's not clear. Okay. So in that case, total B will increase as the shock passes over the fluid if it's a fast magnetosonic wave. Otherwise, in slow magnetosonic waves, B tangential will decrease because this B is moved towards n cap. Okay, so total B will decrease if the perturbations that are traveling in the fluid are that of a slow magnetosonic wave. Okay, I hope this was clear. Are there any questions? Okay, if not, then we'll move on to sample problems. Very easy problems this week, extremely easy problems. Uh, all right. Uh, Select the correct statements. The wave propagation vector, this is in regard to sound waves. The wave propagation vector is perpendicular to the direction of the velocity perturbations. Or the wave propagation vector is along the direction of velocity perturbations.
Along the direction of velocity propagation.
Clearly, it's a sound wave. These are longitudinal waves, right? So the perturbations are along the direction of propagation. So B. Okay. The group and phase velocities of small amplitude sound waves depend on the sound frequency versus they do not depend on the sound frequency.
Do not depend on the sound frequency.
Very easy, very easy. This is just a recap of sound waves. Very small, easy recap of sound waves. Okay. The correct options are B and D. All right. Oh wow, the answer is here as well. Okay. Good. The plasma meter denotes the ratio of the magnetic pressure to the gas pressure versus gas pressure to the magnetic pressure. We clearly saw that beta was indeed given by some P by P square, where P would be the gas pressure, P square would be the magnetic pressure.
B square over 8 pi, I guess.
Yeah, yeah, times some number. It goes as P by P square. Yeah, you're right. Absolutely. So it is indeed that the plasma meter denotes the ratio of the gas pressure to the magnetic pressure. All right. The plasma meter is proportional to Ca square by Va square or Cs by Va. So this is once again easy. Since Ca square goes as P by rho, modulo factors of gamma, and Va square goes as B square, you know from this that beta has to go as C square by V square. The correct options are D and C. Okay. Alright. Consider two systems A and B. The magnetic pressure in A is twice the magnetic pressure in B. The density and temperature are the same in the two. Then you have to choose the correct option. Since First three options relate to alpine wave. Let's look at the third option first. The sound speeds in A and B will be equal.
Yes.
Absolutely. They will be equal. Why? Because sound speeds, once again, given by P by rho, will be given by T by rho. Because P relates to T. And if the pressure and density are the same in the two, the sound speeds will be the same in the two. So D is the correct option. Now let's move to alpine speeds, comparing the alpine speeds in the two systems. Okay. Alright. The magnetic pressure in A is twice the magnetic pressure in B. And the alpine wave is given by what?
P by B squared?
Huh? I'm sorry, there was somebody said something, but I could not.
Hello, is my voice?
Yeah, yeah, it's clear.
Yeah. I said alpine wave is given by P by B squared.
Yeah, so the alpine square is given by some constant b square divided by rho. Absolutely. Right? Correct. Very good. All right. Now, if the alpine wave in A by alpine wave in B, so then this will be a ratio of the magnetic field in A, not square, because well, both are squared in this relation, divided by magnetic field in B. Right? Or am I wrong? Something is wrong, right? Something seems to be wrong, right? Hmm. Yeah, VA square is B square by, oops, what happened? Yeah, VA square is B square by rho, right? So when I'm comparing the alpine speeds in the two systems, I'll compare the magnetic fields in the two systems, right? So then, since the magnetic pressure in A is twice the magnetic pressure in B, and the magnetic pressure goes as B square, the magnetic pressure goes as B square. So then we know that the magnetic pressure in A is the magnetic field in A is root 2 times the magnetic field in B. Because the pressure goes as B square and the pressure in A is twice that in B. So the ratios of the magnetic fields in the two systems is going to be root 2. I hope this is clear. Okay. So this tells you that the correct option is A. The correct option is A and D. Is that fine? Okay. We have to once again choose the correct options. Slow magnetosonic waves become almost isotropic when the alpine speed is much larger than the sound speed.
No.
Correct. That is true for fast magnetosonic waves. In fact, fast magnetosonic waves become almost isotropic no matter what. We just saw that they become isotropic no matter what VA and CS are. Right? So this is not correct. When CS is much larger than VA, the slow magnetosonic waves propagate at a speed much that is greater than VA and smaller than CS
False.
versus false. Absolutely. They propagate at a speed that is smaller than VA.
True.
True, correct. The slow magnetosonic waves, under simplifying assumption of CS much larger than VA or VA much larger than CS, will travel at a velocity which is smaller of the two, depending on what the direction of propagation is. Okay, so this is true. Alright, when CS is much smaller than VA, slow magnetosonic waves propagate at a speed that is smaller than CS.
True.
Correct. So the correct options are C and D. Okay. For MHD shocks, the mass fluxes on either side of the shock will be equal. Is this true? Or is it true that the pre-shock mass flux will be larger than the post-shock mass flux?
No, conservation of mass. So
Absolutely. Absolutely.
should be
That's what
equal.
the jump condition relies on. We equate the mass flux, the momentum, the energy on either side of the shock to be equal. That's what gives us the jump conditions. So A is true. Okay. The magnetic stress needs to be taken into account in considering the conservation of momentum flux.
True.
True. Absolutely. We're doing MST. Clearly. Okay. The pre-shock momentum flux will be smaller than the post-shock momentum flux.
Again, conservation of momentum, so it should be false.
Clearly. Very easy. Very easy. A and B. Okay. All right. Uh, okay. Last question. For a fast oblique MSD shock, for a fast magnetosonic fast mode oblique MSD shock, the magnetic field is refracted towards the shock normal. Okay, let's think about this. If the magnetic field is refracted towards the shock normal, what happens to the total B, total magnetic field? It reduces because the tangential component reduces, right? The parallel component is going to be continuous across the shock front. The tangential component will reduce if the B field is refracted towards the shock normal. But does that happen in fast modes? That's not what happens in fast modes. That's what happens in slow modes. In fast modes, B actually increases once shock is done with the fluid, once shock has passed through the fluid. So what should actually happen is the B field should have been refracted away from the shock normal. Okay, so this is wrong. Okay, for a slow mode with an MHD shock which is oblique, the B field is refracted towards the shock normal.
True.
Correct. B reduces, absolutely, because now we're dealing with a slow mode. Okay, all right. The component of B which is perpendicular to the shock surface does not suffer a discontinuity. Now this is slightly
False.
tricky. The component of B perpendicular to the shock surface does not suffer a discontinuity. Now we are not talking about shock normal anymore. We're talking about the shock surface.
Okay.
Okay, so a component perpendicular to the shock surface will be perpendicular or parallel to the shock normal.
So it should be true. Then it is the parallel component of the B field.
Absolutely, absolutely. So if this is the shock surface and this is n cap is perpendicular to the shock surface. Now we're talking about the component of B perpendicular to the shock surface. So we're talking about the component of B which is parallel to n. And that we know is continuous across the shock front. So it does not suffer a discontinuity. So C is true. Okay. Alright. For fast mode oblique shock, the magnetic field is conserved across the shock. True or false?
As the magnetic field increases in the post-shock medium, it cannot be conserved.
Absolutely, absolutely. Very good. Thank you. This is true and this is true. This is not true. Magnetic field is refracted towards away from the shock normal. So B increases. So clearly this is not conserved. Okay. So the correct options are B and C. So this is all that I wanted to discuss. If you have any questions, please let me know.
This is not exactly a question but a request. Since this course has been being conducted for the last 3 years, will it be possible for you to share the last 3 years question papers so that we can get the practice of how the exam will be, exact exam will be?
Okay, I'll talk with somebody and I'll let you know if they release because I don't have the question papers. If they release it, I'll share it. I'll in fact ask them to send out a mail with the registered students so that they can get access to the.
Okay.
Okay, sure. Okay, if not, I'll stop the recording now.